Greetings, Algebra 2 students. We are getting into a new unit. This will be the last of the new functions that we discussed this year. And the last remaining one, as you can see on your screen there, is logarithms. Now, our objective for the day is to learn to convert between logarithmic and exponential forms of equations. Now, as we got to see a little bit toward the end of last unit on exponential functions, is that logarithms aren't just a function, they're not just an equation, they are also mathematical operations that can operate within a problem. But it's also even a little bit more than that. So we're going to spend the next couple of days exploring the mathematical aspects of logarithms, and then we will get into the functions and start dealing with the same old that we've been doing for the last several units. Now, logarithmic form is another way of expressing exponential notation. Now, what we mean when we say exponential notation is we are talking about a base number raised to a power. Now, we've seen a good bit of that as we went through the exponential function, since that's kind of the way the entire function is structured. But we saw a good bit of it as well doing the growth and decay problems with base numbers raised to certain powers. Now, what we're getting at here, the background or the underlying concept is that any positive number can be written as a positive base raised to a positive power. Now, based upon that fact, what we can do is we can look at plenty of examples. Here are three. There's nothing particularly special about these three examples. They're just three numbers that I happen to pick out. And just proving the point, any positive number, which we have three of them here, can be written as some positive base raised to a positive power. Okay, so for example, 5 can be written as some number raised to a power. Even a decimal point like 0.25 can be written as some number raised to a power. 512, same idea. Now those powers can vary greatly. 5 is a prime number. Okay, he's not really anything raised to any kind of a special power, like being squared or cubed. Okay, but raising something to the first power, that is still raised to a power. Decimal points are the result of other decimal points being raised to certain exponents. Okay, so you can see, you get the idea there. Any number that we can come up with can be expressed as some number raised to some other power. Okay, so the basic structure is this: that some number n can be generated by a base b raised to a power L. Now you may be a little confused or curious, wondering where the L comes from. Okay, we'll get to that here in just a second. Okay, but the vocabulary of base should be something that's very familiar to us. We have been talking about bases raised to exponents for the last few days in dealing with our exponential functions. Now, L, the official term for it, is called a logarithm. Now, we've come to know it as an exponent, and that's fine. Okay, but when you have a number that is a result of a base raised to a power, the power itself is referred to as the logarithm of the problem. Okay, so our format is n equals b to the L, and that is exactly how it is written, or how it is read, n equals b to the L. Now what we're going to see here is that there's another way of structuring this, another way of pronouncing it, so to speak. It can be read as the log with base b to get n is L. The log with base b to get n is L. Now putting that into equation form, then this is written as such. Log base b of n is L. Okay, so this is the equation format of the English sentence that was written on the third line up there. Now, one of the things we haven't really gotten into, but we're coming up on it very quickly, is that logarithms require a base, and you can see it there as a little subscript b just to the right of the abbreviation log. Okay, logarithms exist in multiple numerical forms of bases. Now, we have not seen any of that thus far, and there's a reason why. Just like with a lot of other things in mathematics, when there is not a number written down to the lower right of the log function, then it is understood to automatically be a certain value. And the value that it's automatically understood to be, if there's nothing written down, is a base 10. Now, whether you realize it or not, our counting system that we work with in the world here is called base 10. And the reason it is called base 10, without going too deep into the background of it, it is called base 10 because 10 is the value where we stop counting upwards in a certain column, recycle back to 0, and then carry into the next column. For example, when we start counting upwards from 0 in the units column, the first number we encounter is 1, and then 2, and then 3, 4, 5, 6, 7, 8, 9. Okay, and we are in base 10 because when we reach that 10th entry in the units column, there is not a new number that shows up in the column. That column recycles back to 0, and we carry a 1 into the next column, and that's how we end up with the value 1, 0, which we call 10. And then as you count upwards in the ones column again, 11, 12, 13, 14, 15, all the way up to 19. Once you reach that 10th entry in the units column, we carry another 1 into the next column, and we end up with 20. That's how come our system is called base 10. But in the world of logarithms, the base number can really be anything that it wants to be. Anyway, moving on. This means that the two formats that you're looking at on the screen right now are identical, even though they obviously look very, very different. Okay, on the left side, that's what we call exponential form. Some number is the result of a base raised to a logarithm. On the right, we have a logarithm of base b of a number is equal to the logarithm L. Those say identical things written in different forms. Now this is going to take some getting used to. Obviously these look drastically different from each other, but mathematically they mean the same thing. Now, why two different versions? Well, simply speaking, the exponential form on the left is a more mathematical form, and the other format, the logarithmic format on the right, is more for engineering. And as you go higher into mathematics, you're going to find out there's a very strong connection between the disciplines of math and the disciplines of engineering. Okay, so what we're looking at today is we are focusing on getting back and forth between the two formats. So let's say we are looking at a problem like this where we're instructed to write 4 equals 3 to the y in logarithmic form. Okay, well, until you get used to this conversion back and forth, then I think the best thing, or probably the most the best way to start, is what I'm trying to say, is to identify the 3 different values, which value represents what, and then convert into the other format. Okay, so let's start here. The log represents the exponent, and in this case, the exponent is y. The 3 in this problem represents the base, and the n value, the number, is represented by 4 in this problem. Now, taking these 3 values and these 3 terms, converting them to logarithmic form, what we end up with is this. Log of base 3 of 4 is equal to y. Log base 3 of 4 is equal to y. Now that probably seems pretty strange. It's going to take some getting used to. Okay, another example. This one doesn't have any numbers in it. It's all variables, but it doesn't change anything. The values still represent what the values represent based upon their positioning in the exponential form. So write x equals y to the z in logarithmic form. I want you to press pause on the video and see if you can convert this into logarithmic form. You can use the example above as a template for how to identify the values and then convert it into exponential form. After you think you've got it, press play and we'll see if you got it right. Okay, so walking through the 3 values here, okay, looking at the problem, the exponent z is the log of the problem. The base is y down underneath the exponent, and the n value is x. Okay, so using these, converting into exponential form, that means that we have log base y of x is equal to the number z. Okay, now just like that can be converted, those problems can be converted from exponential into logarithmic form. They can certainly be converted from logarithmic form into exponential form. But once again, until you get used to this, it's probably best that you identify the values one at a time before trying to move into the exponential form. So let's take a look at the values in this problem. The logarithm in this problem is m. It is isolated away from the log. The base of the problem is x in this case. And the n value is 4. Okay, so using that information and converting into exponential form, we have 4, which is the n value, is equal to the base raised to the logarithm, that is x to the m. Okay, once again, I'd like you to take this generic example using these variables, and I'd like you to convert log base a of b equals c into exponential form. So once again, press pause, identify your 3 different variables and what they represent, convert it into exponential form using the example from above as a template if you need to, and then press play and we'll see if you get it right. Okay, now in this case, the log is going to be the c value, the base is the a, and the n value is b. Okay, so our n value is b, so b equals the base in this case is a raised to the logarithm, which is c. So hopefully you arrived at b equals a to the c. Now obviously these equations, these formats, exponential and logarithmic, they have 3 variables in them. So if we know any 2 pieces of information to fit into those formats, we should be able to solve for the remaining piece of information. So let's look at a couple of examples where our variables may be moving around. So for example, let's say we are told to solve log base b of 8 equals 3. Now, hopefully, as you should know well by now, in order to solve, that means you need to get the variable by itself. Well, at this point in time, we have no idea how to get a base number off of a logarithm in order to isolate that base number, because that's where our variable is at. Okay, but one of the new tools that we have at our disposal is the fact that we can convert this problem out of logarithmic form into exponential form in the hopes that having it in exponential form will be easier for us to solve than the format that we are looking at right now. So once again, let's identify our particular values from the problem. Our logarithm is 3. The base is b, as we've already said, which makes our argument, or the n value, 8. Converting those three values into exponential form, we have an equation that says 8 equals b cubed. Now, in the original logarithmic form, I doubt anybody had any idea what the value of b might be. However, in exponential form, I imagine many of you have a real good idea of what b is going to be now. We are simply more familiar with this particular format, and a lot of our brains can go ahead and calculate this out. However, if you are still in a little bit in the dark on what b is, obviously you can see that b is being cubed. We don't want b to be cubed, we want it to be b to the first. So we have to get the 3 off of the exponent of b. Okay, so obviously if the opposite of something being cubed is the cube root, so we want to take the cube root of both sides, or in short, what we want is currently we have an exponent of 3 over 1, so we are going to introduce a new exponent into the problem, both sides of the problem, of 1 over 3. And the reason we're going to do that is because of law 3 of the laws of exponents. If you have a power raised to a power, then the rule is you multiply those exponents. 3 times 1/3 on the right side there is going to make an exponent of 1 for our b, and that's what we want. On the left side, 8 raised to the 1/3 power, or the cube root of 8, is 2. 2 times 2 times 2 is 8. That's what a cube root means. What number times the same number times the same number again gives you the value underneath the radical. Okay, so in this case, our b value was a 2. Okay, these problems can do a lot of different things, and the variable can move around. Here we have another one, and the variable's in the same place. It is the base that is unknown. So let's look at it again, make sure we understand. Okay, again, we probably have no idea what the value of b needs to be so that this problem can equal -1/2. So a good strategy would be to convert it into exponential form and have another look at the problem. Okay, so let's identify the values. The log is -1/2, obviously, from the problem. The base is obviously b from the problem, and that leaves our n value to be a 9. In exponential form, that would be base b raised to the -1/2 power is 9. Well, we're in the same spot again. You may remember me telling you last unit that the 1/2 power is the same as square root. Okay, so we have the square root of b. That means to get rid of the square root, we're going to do the opposite of square root, which will be to square both sides of the problem. However, also look and notice that our exponent is currently negative. We have a -1/2, which means when it comes time to introduce our new exponent, we will always also want it to be a negative value. Okay, because remember, these exponents are going to multiply. We want a negative times a negative to be a positive. Okay, so by bringing a -2 in there, on the right side, -1/2 times -2, that'll be +1 for the exponent of b. That's what we want. Now also, on the left, notice that our exponent is negative, 9 to the -2 power. One of the rules of the laws of exponents we talked about at the end of last unit. Some of y'all missed it, and that is dealing with a negative exponent. You remember what a negative exponent does? Okay, a negative exponent is basically telling us that our value, our base, is in the wrong part of the fraction. Okay, right now our 9 is in the numerator, but it has a negative exponent. That's telling us that our 9 wants to be in the denominator, and by moving it to the denominator, the exponent goes from negative to positive. Okay, so as you can see there, 1 over 9 squared, and of course 9 squared is 81. 1 over 81 is our value for B. Now this is going to take a little bit of getting used to, especially going back and forth between logarithmic and exponential form. Okay, and then learning to use that in order to assist you in solving a problem. So I appreciate you finding time to get your notes taken care of, and I will see you in class.